Clearly, it doesn't really matter whether we are talking about passenger cars or ships or aircrafts or even off-road vehicles like mining trucks. These are diesel guzzlers, gas guzzlers, right? They consume a lot of gasoline or diesel, right? So basically, there's a huge impetus to convert them into electric or hybrid electric. So around the world, electrification has started. It's only a matter of time before that catches up, right? So if you are learning about electric motors, there's no better time to do it. Whether you are learning about electric motors for condition monitoring or not, that is secondary. And all these electric vehicles will need chargers. So if you're working on DC-DC converters, so you know your job is cut out. So all your research is quite relevant, right? So that is give you. So we can have motors like this in an electric car. So a typical motor will be this size maybe in an electric car, 80 kilowatts power range. To a ship propulsion motor, which can be as big as this, bigger than a human being. So few megawatts of power, right? So we are now talking about, when I say propulsion system, this is what I'm trying to show you. It can be small motor or it can be a big motor. And if you're talking about electric scooters or electric motorbikes, the motor size even diminishes. So we are talking about something that is only as big as your palm to something as big as like a giant wheel, right? Like it's a big motor. So the different parts that make up the motor, most of you would be very familiar with them as an electrical engineer. So we have your rotor, we have your stator, bearing on both ends, there is a shaft, and then they have end bells. Then we have a cooling fan typically. This is a very standard diagram, right? So I hope all of you are familiar with the terminologies. Don't need to worry about that. Nothing in the world is perfect. Electric motors are no exception. So they are also prone to failure statistically, as given by IEEE or as collected by EPRI. Electric motors. So these are data collected from industrial environment. Okay? These are not data from electric vehicle application. So that is the biggest information I want you to keep in mind. Whatever data we right now have is based on the data collected of operating motors in industries for several decades, multiple decades, more than a same, like 60 years, 70 years, like that. But we do not have any data for electric motor failure from electric vehicle sector yet, because it's just coming up. Maybe 25, 30 years later, we will have better data pertaining to electric vehicle market. Excuse me. As you can see, the major reason for failure in electric motor is bearing. It's a gradual failure. Usually when bearing fails, it will not fail instantly. It is going to decay, deteriorate, and then fail one day. Winding faults is another major source of fault, but this is an instantaneous fault. Insulation fails, you get a short circuit, and then the motor is burnt. Instantaneous. It's quite dangerous. Eccentricity faults, which is the focus of this workshop, is also a major reason for motor failure. It constitutes about 15 to 20%. And then there can be other types of faults happening in the rotating element, which can be, in case of an induction motor, it can be broken rotor bar, or in case of a magnet motor, it can be demagnetization of magnets, something like that. Okay, so it's different. So if you look into a chart, so there's 40% of bearing faults, 30% of winding faults, 14% of eccentric faults, and 9% of rotor faults. So the question naturally that probably comes to all of your mind is, hey, if this is the spread of faults, why are we talking about eccentricity faults, right? We should be talking about bearing faults, or we should be talking about the winding faults. There are two reasons. bearing faults invariably lead to eccentricity. Okay, so bearing fault is not an instantaneous fault, so it deteriorates slowly. As bearing fault progresses, you will see eccentricity in the machine. So when you can detect eccentricity, you are also indirectly diagnosing bearing fault. Okay, that is one of the reasons. So imagine you club 14% and 41% and put them together into one bracket or one chart, then that is the fault we are actually looking at, but we start by detecting eccentricity. Okay? So we may have to do a lot of research how to segregate once eccentricity is diagnosed. What is the cause behind it? Is it a bearing related cause or is it a non-bearing related cause? Has to be diagnosed. Okay? So segregation is a challenge. So that is why I need researchers, right? We need researchers to come and work on that. Another reason is a matter of convenience, to be honest. The winding faults, as I said, they progress rapidly. They progress rapidly, instantly. So what does that mean? Is you cannot have an offline winding fault detection scheme. That means if a motor is working, you have to sense winding health while it is still working and on a continuous basis, because you never know when it will fail and there is no time available for you to sense, act, because it's instantaneous fault. Whereas with bearing and eccentricity fault, it's more a gradual fault. That means it gives you the luxury of time. So you may have days, you may have months before it actually worsens to a stage where the motor's performance is completely compromised. Motor would be performing poorly, but it's still performing. It is like you want to secure 100% on an exam. Not every time you can do that. You get 85%, 95%. It's okay. You are still okay. You are not perfectly happy, but you are happy. But sometimes you have a bad day and you don't do really well on an exam. You don't score many marks. You don't pass the exam, right? So that's the worst case for you, right? So the bearing fault can result in such failures too, but that is the worst case. So we have lots of time between when a bearing fault or an eccentricity fault starts to when a motor would lose its performance completely. Okay? So we have that luxury of time. So because of that convenience, we have ability to diagnose it using different techniques. Okay? If it were like instantaneous fault, then this workshop probably would not have much sense, because we have no time to do all those things that we want to do. But now there is luxury of time, we can try out different things. Okay? So this is main idea I want you to have in mind. So just to give you some visualization, a stator fault. I mean, this is a good looking stator fault. Some of the real world stator faults will be more bad looking than this. It will be completely burnt. In fact, one of the ferries that go from where I live, Victoria, to my airport, which is on the mainland, it had a stator fault, and the motor was thankfully it was not when the ferry was sailing. When it was docked is when they started, it failed, and therefore there was no major issue. But imagine motor failure like that while we are sailing middle of a deep sea. Then we need to wait for another bigger or more powerful tugboat to come and tug a vessel to the dock, right? So it's going to be a pain. So it's just to give you an idea, rotor bar fault can be like this. Just because of electromagnetic forces acting, your mechanical strength is tested all the time. Okay? And with age, material give apart. So this is another issue. So rotor bars in an induction motor can break just because of stress the machine has to undergo. Okay? So this is just to give you an idea of what different faults are. Okay, so now until this point I have given you a general picture. I want you to understand that I want you all to be convinced by now that electric motors number is going to increase. Even if 10% of electric motors have eccentricity fault, with the numbers going to increase, 10% means a lot. That means learning about it is important, is useful. Okay? So you should convince yourself and your immediate neighbor that yes, this is an important topic to learn. Okay? So what is eccentricity? So that's the first question we are going to learn in this course. Probably open it up. Does anybody know what eccentricity means already? Yeah, please.
Stator and rotor centers are not aligned with it.
Okay, stator and rotor, that's precisely what eccentricity is. Anybody else has a different way to say it? Okay, so I will give you a typical definition. Imagine that the blue color circle here is the stator of an idealized machine, and the green color circle here is the rotor of that idealized machine. In a perfect world, their centers should coincide. If C1 and C2, so if I go back one slide, C1 is the center of stator. So we are looking at one view, right? It's basically a three-dimensional object, right? We are only looking at the front view. So C1 is the center of stator and C2 is the center of rotor. And if they both coincide in an ideal world, what we will have is a healthy motor. What does that mean? If this is the distance between the inner surface of the stator and the outer surface of the rotor, and if I call that as air gap, if I position myself on this blue color circle and if I walk around, I should see the same distance no matter where I am along this circle. Right? Do you all agree? So this is called as a uniform air gap. Okay? Because as I go around the stator's inner surface, the distance will not change. So if I plot it with respect to angle, so the distance or the gap in length, usually its unit is in meters or standard unit is in meters, versus the angle, if I go around the stator surface, it can be in degrees or radians, doesn't matter. So you will see that irrespective of the angle, the length remains same. So this is normally or ideally what we expect in a motor. Okay. But what is eccentricity? Eccentricity is when the centers C1 and C2 do not coincide. The two circles are placed such that the centers do not coincide anymore. What does that mean? The gap around the stator's inner surface or inner periphery is no longer a constant line. Right? So if I position myself on the inner periphery of the blue color circle and if I walk around the circle, I see that the distance will start at a minimum value. If I go from this point, it will increase until a maximum point and then it will go down. As soon as I can see this, I can say this is a sine function with a DC offset. So it's a shifted sine function, right? Mathematically speaking. So if I have to write a mathematical expression, it should have a DC component A0 plus a magnitude A1 times sine or cosine, if however you want to call it. That's fine. So this point where the gap length is minimum is called as the point of minimum air gap. And the other end would be the point of maximum air gap. Okay? So is this clear? So what is eccentricity? Eccentricity, as one of you mentioned, is basically the condition in which the centers of the stator and that of the rotor actually do not coincide. Can you think of a reason why that could happen? Anybody? Why should they not coincide? So manufacturing issue, right? Say for example, if I am manufacturing the stator, if I cannot guarantee to precise micrometer dimension a rotor, a circular structure, there is ovality. Right? If you try to draw a circle by hand, you may not get a perfect circle, right? You may get an ellipse or an oval. So if the manufacturing tolerances are poor, then you may not get a perfect circle. You will get an oval. That could be one reason, right? So if you have an oval, then the center is no longer C1 in you. It is offset somewhere here and there. Right? So it's going to be difficult. So that's a very common reason. What else can you think of? Like manufacturing is definitely one of the reasons. Anything else? From an operational perspective, uneven flux distribution, stresses are not uniform. It's probably because of the design. Some side carries. So if the winding, if one coil has lower resistance than the other by a small value, then it will draw more current, it will produce more flux. So it can have a variety of reasons. But any other non-electrical reasons that you can think of?
Wear and tear of a machine.
Wear and tear of a machine, yes. This is all true.
Pressure on soft.
Sorry?
Pressure on soft. Rotor soft.
Pressure on the rotor shaft, load, yeah. But if I give you the stator and the rotor to you, bearing, shaft, everything, and if I tell you to put them together, do you think there can be a source of error in making sure that the centers are not aligned? See, when you are assembling, right, manufacturing is one thing. When you are putting things together, you can see if you are tightening a screw, you can tighten the screw perpendicularly or at an angle, right? You can make a mistake. That is your error. That's very common mistake. So just like that, when you are assembling motor, you may not align. In fact, many of the cars, they do wheel balancing, right? Why? Because when they remove the tires and wheels and then put them back, they want to make sure that the wheels on either side are balanced, right? And they are not heavier on one side, they are not tilted, all those things. So the assembling part itself can introduce error. So it's not just manufacturing issue, it can be assembling issue as well. So what I'm trying to say is, when we have only large industry grade motors, the manufacturing and assembly processes are very stringent. You would not expect any major source of error. The reason being these are expensive machines, these are bigger sized machines, and the regulations and the standards and the specifications will be very, very strict. When we are looking at a motor for an electric two-wheeler, the main thing that we are looking to save is money, cost, right? When we are buying electric two-wheeler, the first thing we will check is the price. Then only we will check about its performance. Right? Same thing for passenger car. The cost competitiveness, the first thing that will take a hit is that specification. The manufacturing tolerances will be increased to reduce cost. The assembling stringency will be compromised to mitigate expenses. Okay? So these are some common things that will happen. So that means the source of eccentricity fault is going to be more pronounced. So the percentage share of eccentricity fault in motor failure is going to be more as we see more and more electric vehicles coming up, because we are going into a cost competitive market. Unlike until now, where we are looking at electric motors operating in industrial setting, where cost is like last thing, it's not a major thing. We want perfect functionality, it's critical element, everything has to be precise, perfect. Okay? But now we are entering a cost competitive market. Okay. Anyway, so this is the basic definition of eccentricity. I want you to understand that eccentricity, when you have the center of stator and rotor offset, we have a situation now which results in what is called as different types of eccentricity. We have a fourth type too. I should write it down. I will explain it after I complete explaining these things. There is something called as a static, and there is something called as a dynamic eccentricity. Mixed eccentricity is basically the appearance of both of these faults, static and dynamic eccentricities. Okay? So let us try to understand what is static eccentricity, what is dynamic eccentricity, because these two terminologies we will continuously use throughout the workshop, and if you are planning to pursue research in this field, you will have to understand them very clearly. So static eccentricity means an eccentric fault condition in which the center of the rotor is exactly the center of rotation of the motor. So the rotor is rotating about its own center. Okay? But the center of stator is offset from the center of rotation. Okay? So just to give you an idea, let us look at this. So we have a center of rotation, which is the center of rotor, but the center of stator is offset. Right? Is this, can you understand this? So this type of eccentricity fault is called as a static eccentricity fault. Why is this called as a static fault? Is because the point of minimum air gap. So if I walk around the inner periphery of the stator, the point where I will see the minimum air gap remains fixed in space and time, of course. It does not change in space or time, right? So if I walk around once, twice, thrice, I will always hit the minimum air gap point here at this position. So because it's stationary, that point of minimum air gap, I am calling this as a static eccentricity fault. Okay? So now I will give you a small exercise. It's going to be a little bit tricky. Instead of walking around the stator inner periphery, because I have been walking there, it's crowded, you are now going to take different rotor bars as the place to locate yourself. Imagine you are sitting on different rotor bars in the machine. Okay? So imagine yourself, one of you is sitting on the orange color bar. One of you is sitting in the maroon or red color bar. One of you is sitting in green color bar and other colors. Okay? What I want you to do is take a few minutes. You can even discuss. It's not an exam question. I want you to plot how you would perceive the gap to change as the rotor is rotating. So I want you to come up with a plot of the gap length as seen by you sitting on a rotor bar as the rotor is rotating. So as you complete one rotation, one full circle, I want you to come up with a diagram that will plot the gap length seen by you. You are now sitting not on this chair but on the rotor bar. Okay, so I'm going to give you a couple of minutes. Visualize, discuss, think. Then all I'm expecting is a plot of air gap length. Okay, let us say, just for ease, imagine you are on the orange bar and you start along this position initially, the x-axis, just for consistency. Otherwise you may come up with different plots, right? So imagine you are in the orange bar and you are going to sketch the gap length seen by the orange bar, or you sitting on the orange bar as the motor is rotating one rotation. So I want you to plot angle, let's say in degrees, it will be easier, versus gap length in meters. For the orange bar, as you are sitting on the orange bar and as it is rotating. Okay, so I'll give you a couple of minutes time. 11:25, 3 minutes. You are welcome to discuss, chat, agree, disagree, fight. Anything is fine. If you have any questions, do not hesitate to ask, okay? I'm here. If I know, I will answer. Otherwise, I will try to find the answer for you. Don't worry. So if some of you have already drawn for orange bar, anybody has already completed? You have already done? Okay, that's good. So you can sketch for another bar, say maybe the red color bar on the same plot, so that we can see how it looks like. So I want you to...
Sine waveform, like
Yeah.
sine and then cos wave.
Yeah, exactly. It will be a sinusoidal waveform. I just showed you the waveform 2 slides ago. I want you to plot it, but
180 degrees.
it will be slightly different.
180 degrees phase.
So the orange color bar, if I really look at it, it starts at the point of minimum gap, and then as I am rotating, I am sitting on the orange bar and then I am traveling, the gap continuously seems to increase and then it decreases. So this is for orange bar, right? So this is how the gap diagram will be. But for the red bar, it will be the other way around. It will start at a maximum point because the orange bar is here, the red bar would be at the other end. So it will start here and then it will go down and it will go up. So what will happen to the green bar which is in between? So if I take the green bar on top as a starting point, then it will start somewhere in between and then it will have, right? So basically we have phase shifted sine waves or cosine waves, right? Do you all agree? So this is clear, right? So why I am saying this is, it's very interesting. Static eccentricity means when I am walking around the periphery of the stator's inner surface, the position of minimum gap will not change in space or time. So that's the definition of static eccentricity. But if I situate myself on the rotor surface, it is going to change, right? So depending upon which frame of reference you are using, things will change. So later on in today's lecture, I will use between stator frame and rotor frame, and you should understand that it is important that when you are going from one frame to another, things change a little bit, right? Okay, so this is what you would have got for orange bar and red bar. So this is static eccentricity. Now let us look at the next type of eccentricity called as dynamic eccentricity. So dynamic eccentricity means the center of stator coincides with center of rotation of the motor, whereas the rotor center does not coincide with the rotation of the motor. Okay, so it's a slightly different. So center of stator coincides with the rotation of the motor and the center of rotor is not coinciding. So what does that mean? Your dynamic eccentricity will look like this, right? Your motor is rotating about stator center, not about rotor center. Is this understandable? See, all these diagrams are exaggerated just for us to understand. Right? In real world, the gaps are so small that we may not visualize such big motion. I mean, a motor can never operate under such condition. You will have rub already and fire maybe by in a couple of minutes there will be smoke coming out of a motor like this. But just to give you an idea. Okay, now you know the exercise. So why is this called as a dynamic eccentricity? Because if I walk around or if I situate here on the stator's inner periphery, At some time, the minimum gap comes here, but at some other time, the gap increases to maximum gap. So, even though I am here in the stator inner periphery, I perceive the gap to change with respect to time. So, that is why it's called as a dynamic eccentricity. Okay. So, now the exercise for you is, don't be on the stator inner periphery, situate yourself on the rotor bar. So, start with the orange color bar, again start along the x-axis as the starting point. Try to plot the gap in length, gap length in meters versus angle. Again, you are free to discuss. There's nothing wrong in discussing and agreeing to an answer. So this is an easier answer, right? You are all already saying that. So it's a straight line. So the bar that is starting at the maximum gap position will continuously have maximum gap. Bar starting at the minimum gap position will continuously have minimum gap. And any bar in between will have that in between value. But this is continuously constant. Okay, so it's very strange that the name static and dynamic eccentricity are given from a stator frame of reference, but when we plot the gap from rotor frame of reference, they are completely the other way around. Right? Your dynamic eccentricity's gap length is constant for a particular bar, and static eccentricity is gap length. So what is mixed eccentricity? Mixed eccentricity is nothing but a combination of these two. What does that mean? Your center of stator and center of rotor are not coinciding, that is eccentricity by default, and the center of rotation is another third point now. It's neither of these 2 points. So that means neither the center of stator nor the rotor coincides with center of rotation. So it will be somewhere in between. So now it's a very tricky situation for us to visualize, right? Like cap. So if again I'm going to ask you the same exercise. So try to situate ourselves here in the inner periphery of the stator. I see that the gap changes with time. The minimum gap changes with time. So it's not static fault, it's a changing fault. But if you plot the gap length seen by the orange bar with respect to time or with respect to angle as you go around, you may not get a constant line. Right? Do you agree? Like, locate yourself on the orange bar along x-axis to begin with, and as you go through, what happens? Things change, right? The gap length changes. It either decreases or increases. Doesn't really matter. So what I'm trying to say is, these are not color-coded by any means, but ideally you start at some value which is neither minimum nor maximum for a particular bar, and then you change and you come back. So the difference between static and dynamic eccentricity, mixed eccentricity is, in static eccentricity, each of these plots are just phase shifted. They are not level shifted. In dynamic eccentricity, each one is just level shifted, not phase shifted, right? Because it's DC. But mixed eccentricity is combining these two. That means they are both level shifted and phase shifted, right? Mathematically. So you can actually write an expression already the way you are seeing it. You can write A0 plus A1 cos phi or something like that, plus another phase shift angle. Okay. So these are the different two types, static and dynamic, and mixed is a combination. Okay, I want to introduce you to another type which I have not included in my slides, and the reason is we are not going to focus on it, although this is a common fault. It's not something which you will not encounter, but this is a fault you will encounter as well. But I have not, the workshop is not focused on it. And this fault is called inclined eccentricity. So all this while we have been looking at 2 dimensions. We are looking at the front view, right? Now imagine the 3rd dimension. So let us say this is the stator, but the rotor is somewhere like this. The shaft is like this. Okay, what does that mean? So along the length of the shaft, if the bearing is moved on one side, right, you get a tilt. So this eccentricity is called as an inclined eccentricity. You might be familiar. Hydro generators, you have learnt about that, right? How are they mounted? Like how, if you have to draw a hydro generation plant, they are vertically mounted, right? The shaft actually goes vertically. So what does that mean? All the load has to be borne by one particular bearing at the base. So there is a high inclination or high possibility of having a tilt, right? It's very normal. Again, it's rare, but it's possible. So in any motor there is a driving end and a non-driving end. DE and NDE. NDE stands for non-driving end. That means the fan will be attached, but the load will not be coupled. Okay? So it's very common that the driving end you will see some higher load and the shaft is kind of going on one side. Okay? So the inclined eccentricity is not uncommon. But in this course we are not going to focus on it, simply because it is a 3rd dimension and it complicates matter. But the tools you are going to learn in this course will equip you to analyze this system, this condition as well. It is just a matter of you trying to apply that. Okay? So this is the 4th type or 3rd type. Static, dynamic, inclined are the 3 types. Mixed is a type where we combine static and dynamic eccentricity. Okay? Okay, so now when does eccentricity or the change in the offset between stator and rotor centers become a problem? When is it considered a fault? Right? Some degree of variation will always be there. Like if you measure in nanometers, picometers, you will see obviously some offset, right? At what dimension you are saying this is becoming a problem to me? So that question has to be answered. Okay. So typically literature says for industry grade motors, eccentricity is considered as a fault only when the variation in the air gap is more than 10% of its uniform air gap value. So under healthy condition, if the air gap is, let us say, 1 centimeter, which is 10 millimeters, the machine is considered to be under eccentric fault only if the air gap variation is greater than 1 mm, which is 10%. If the air gap variation is less than 1 mm, we are not considering it to be a fault. It's okay. Okay, so that's the idea. Just 1 mm, 1.5 mm out of 10 mm is a small fault. Machine will still operate. There will be no problem. Performance might get deteriorated. You will hear increased noise. You may see higher vibrations. Okay, these things will happen. So these are again for industry grade motors. That means the air gap is quite large. Industry grade motors means motors of higher power and their air gap is at least like 10 mm, around a centimeter or more, maybe more than that, 15 mm, like that. Okay. And based on industrial data, mixed eccentricity is the most common form of eccentricity. That means whenever there is an eccentricity fault, it is always combination of static and dynamic. It's not purely static or purely dynamic. Okay. So one thing that we discussed initially is manufacturing reasons, assembling reasons we can have fault, like eccentricity fault. Some of you mentioned that during the operation due to wear and tear or aging, things may not be aligned. So the dynamic eccentricity happens when the shaft is no longer precise, it's bent, small bending happens, or bearing has some fault, dynamic eccentricity shows up. Okay? So these are all due to wear and tear. Okay? So typically most of the bearing faults will result in some kind of dynamic eccentricity, and the manufacturing tolerances will introduce static eccentricity, and therefore mixed eccentricity is the most common form of eccentricity you will see. Okay? So what is the problem? Why eccentricity fault has to be looked at? Because of the non-uniform variation of air gap, right? The magnetic pull on one side will be higher than the other. Wherever the gap is shorter, the magnetic forces of attraction will be larger, right? Obviously, because of asymmetry, you will have higher vibrations and noise. Sometimes if you allow higher degrees of dynamic eccentricity, if you recollect the slide I showed, this kind of motion, when you allow this kind of motion to persist, with time what happens is the unbalanced magnetic pull is so large that the rotor can go and rub against the stator. Momentarily. It will not be a continuous rub, it will be just momentarily rubbing once. Okay? So that is what we call a stator rotor rub, and this is what it will look like. So imagine 3000 RPM. That's it. You have to bring down the motor, right? Electric vehicle motors are operating at least at 3000 RPM. Under some operating conditions, they can go at much higher speeds. 12,000 RPM, 13,000 RPM. Okay? So you have to keep that in perspective. So the problem with eccentricity fault is, even though it's gradually deteriorating, it gives us the cushion of time. It's not going to start today and result in a rub immediately. But if we don't monitor it frequently enough, like if we don't assess the situation, over time, there's a high chance that it may result in rub. Excuse me. So what is the problem in diagnosing eccentricity faults? The first problem is almost all modern EV motors, excuse me, have much smaller air gap. Modern EV motors have much smaller air gap than industry grade counterparts. So in industry motors, if we have 10 to 15 mm, now we are talking about 2 mm air gap length. Why? You have to fit the motor within the car, right? You cannot have a car which is bigger than the lane. You have to put everything within a compact space. In factory, you accommodate real estate, but in car, you cannot. So the compactness matters. So the size goes down, the gap length goes down. Okay? And because even though the mixed eccentricity is the most common form, let us say we have diagnosed it. There is mixed eccentricity. We know mixed eccentricity comes due to static and dynamic. Static could be due to some problem, dynamic could be due to some other problem. So our challenge now is we have to segregate the two and identify its severity independently. If there is a mixed eccentricity fault, which one is more dominant? Is dynamic more dominant or static? If dynamic is more dominant, then let's look at bearings. If static is more dominant, let's look at something else, right? So this is a problem. So we are given a signal or given a condition which is a combination of two scenarios. Unfortunately, the causes for the two scenarios are totally different. So from that one mixed eccentric operating condition, we have to diagnose whether it's not static or dynamic, how much they are, what could be the cause for it. Okay. So this is a big challenge. So the air gap length shrinking and the fact that mixed eccentricity is the typical form, while the causes for static and dynamic are completely different, means, see, the goal of condition monitoring is to resolve the issue. The sooner we can resolve, the better it is, right? So if I can diagnose and tell exactly, okay, this eccentricity is due to bearing fault, then technician will quickly work on the bearing. The downtime is reduced. And that's the goal of condition monitoring. So these are the major challenges. Okay. So is this clear? Awesome. So what I'm going to do now is I'm going to give you 5 minutes break. Okay. So it has been 1 hour since I started speaking. So I should let you. Second year or even high school physics is what is being applied. Okay. So that we will learn after. Okay. So we are going to do it in a different style. So after the break, so at noon we will meet again at 12 noon, and we will get started with how eccentricity fault has been diagnosed, basically. Thank you. And in this session, I will be speaking less, and you are going to interact amongst you. Okay. So I have presented until now what eccentricity is, right? So you basically understand that if there are two structures, so this is like a rotor, and this is a stator. This gap is no longer uniform. That's the problem, right? So what I'm asking you now is going to go into smaller groups. I see that we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So maybe you can divide yourselves into 3 groups of 3. Okay. And then what you will be doing is you are going to come up with some ideas as to how we can identify this non-uniform distribution of air gap length. So what I want you to think about is, come up with an idea. Okay, I have given you a motor, it has non-uniform air gap length. I want you to come up with a method or a means. It need not be a method, a means, a thought, an idea as to how you can identify that this gap is non-uniform. Okay. So to give you some guidance, what I'm going to do is I'm going to share this information first. So traditionally, as I said in the outset today, that I'm trying to condense multiple decades of research, right? So when I summarize many years of research, I can put this in on the single slide as eccentricity fault detection or diagnosis can be categorized into 2 broad schemes. One is invasive method, using invasive method. Everybody understands what invasive means? Invasive? No?
Using a sensor.
Using a sensor, but invasive means something that goes inside the motor. Okay? And non-invasive means, again we are using sensors, but not inside the motor, outside the motor. That's the only difference. So our GIAN workshop title is non-invasive fault diagnosis, right? So we are not interested in invasive fault diagnosis. Invasive means placing sensors inside the motor. Okay? So traditionally, historically, invasive sensor-based eccentricity fault diagnosis has been widely used. Okay? I will give you this insight or a snippet, and I want you to focus on this aspect. So invasive sensor-based monitoring can be done using two methods, broadly speaking. One is, we are placing sensors to measure the gap, the physical gap, right? So I want to somehow measure. Say you take a tape, measure, walk around. It's possible, right? If you have a hydro generator, the circumference of the stator is as big as this classroom. So we can walk around the surface and we can measure the distance by having a tape, right? So that is one method of measuring gap around the rotor. That is a gap measurement technique. The other technique is also invasive, but it does not measure the gap, but it measures a quantity inside the motor, like air gap flux density, something like that. Okay? So there's a fine difference. We are placing sensors inside the motor, but the purpose of placing sensors can be completely different. In one set of applications, we place sensors to measure the physical distance between stator and rotor. In another application, we are placing sensors to measure a physical quantity of the motor, like flux in the air gap, or flux along the shaft, or voltage produced along the ends of the shaft, something like that. Okay? So they are all sensor-based techniques, but the sensors are placed inside the motor, and that is why they are called as invasive condition monitoring techniques. And the invasive condition monitoring techniques can be categorized into two types: physical gap measurement based or an air gap quantity measurement based. Okay. I see that we have new participants. Welcome both. So we'll do a quick introduction of you first, so that we know everyone, and then you can also quickly introduce yourself just by saying your name and affiliation, so that they are aware who you are. Okay, so please, sir.
Sir, good morning, Mandal. Then here, myself, Dr. Ilambu Dr. Swami from Amateur Physical Campus, and Associate Professor, PS Associate Professor. Very nice to see you all in this workshop.
Thank you, sir. Thank you so much.
Good morning, all. My School of Engineering. I'm working as a professor there.
Thank you, sir. Thank you. So we quickly go around the room once again.
Yes, myself, Venkataraman Naik, currently working as associate professor in NIFD, and so working on EV charging, fast and extend EV charging for domestic application. And I realize the renewable and then
Myself, Jayashree Moda. I'm a PhD scholar in NIFD.
Myself, Raghavendra. I'm a tech student and NIFD.
Myself, my name is Bharat. I'm a tech student. Myself, Bharat. I'm a PhD scholar and BA professor BA National.
Myself, Harshit, doing MTech first year in NIFD in PE.
myself, Srinivas. I'm doing MTech first year in NIFD.
I am Krupakar. This is Kaur, working under Vidya Division and Vidya National.
Thank you so much. So the reason why we did this introduction is twofold. Because I don't want you to be completely unfamiliar. Okay, so since we have two new guests, we will break them down into two different groups. So one of the goals of the smaller group is also tell them what eccentricity is based on the information you acquired. And then, if I'm not wrong, you all should have received 3 PDF research articles, right? You all have access to it, right? So we will go in ourselves into 3 groups. We want to 3, 4, 5, 6, 7, 8, 10, 11, 12, 13. We have 13 members, so that's 3 groups of 4. One group can have 5 persons, that's fine. So we'll break into 3 groups. You both will be in 2 different groups and not necessarily in the same group. And then, so there are 3 research articles. Each group is going to focus on completely different research article. Okay, and you are going to talk. I will give you instructions as you go. So first, you are going to form smaller groups. So maybe identify 3 or 4 people that want to work together, and then I will give you a paper, and then we will talk about what invasive method that paper is going to focus on, and as a group you will learn about it. Okay, so who wants to be in a group? You can decide now. 4 people, like you can raise your hand or you can stand up. So those 4 people, okay. So maybe one of you can join them, sir. So you can go to the other row and so since this is a big classroom, you are welcome to. No, sir, you can join them. You will be a group of 5. That's fine. So we'll have 1 group of 5, 2 groups of 4. So since this is a big class, feel free to spread out once the groups are formed, because you are going to discuss and you don't want to disturb others. Okay? Okay. So 1, 2, 3, 4. Okay. So the 4 people on the left, so you can probably sit apart a little bit, and you 4 can maybe go 1 row back, so that when you discuss, you are not interfering with others. Okay? Excellent. So if I'm not wrong, there are 3 research articles. It says paper 1, paper 2, paper 3, right? So the group up front will be discussing about paper 1. So we have 2 new participants. That's good. Each one can join a group. So you can, ma'am, you can join that group there. Yeah, and you can join the other group there. So now we have 3 groups of 5. That's even better. So no advantage to anyone. So the group over there is going to go into article 3. So paper 1, paper 2, you are paper 2, and then paper 3 is on the other side. Okay. So what I want you to do is, so it's 12:13 now, so I'll give you time until 12:30, 17 minutes. That's a fairly long time. You don't have to read the entire article. You are just going to go into the methodology and see what. So the focus of the 3 articles are just this section. Invasive sensors. So they either measure a physical gap or they measure the physical quantity inside the motor. Okay. So what you have to first do is go into the article, try to identify what is the actual measurement about. Is it a physical gap measurement or a quantity measurement? If it is gap measurement, what technique is being used? If it is a quantity measurement, what technique is being used? So just try to summarize that methodology in your own words. Okay. So you have 17 minutes time. You can discuss amongst yourselves. The idea is to interact and learn what this paper is about. Okay. So is the objective clear to everyone? And for the 2 groups that have, like pretty much every group has a new member, right? So maybe you can take 2 minutes to explain to new member what eccentricity fault is first, so that everybody is aware, and then from there you can get into the research article. Okay. So I will stop at 12:30. So you have time until 12:30 to do this exercise. Give it a try. Let's see how this goes.
Sir, can you repeat again once?
So the objective is you are assigned paper 3. As a group, you will be looking into paper 3 and identifying if this article is focusing on a physical gap measurement or a quantity inside the motor measurement. And then once you have identified what it is exactly trying to measure, you will also try to understand the method or how that is being measured, the methodology. So just focus on the methodology of the article. You do not have to read anything else, just focus on the methodology, just get a basic idea of what that paper is focusing on. Okay? So just the methodology section of the research articles is the focus. Okay? So paper 1, paper 2, paper 3. Paper 1 is, wrong window. Paper 1 is this topic. Paper 2 is online detection. Paper 3 is, okay. So just by looking at the title you should get an idea already, but you are welcome to read the abstract and the methodology to get a clearer picture. Okay. So the idea is you do a quick reading, discuss as a group.
They anticipate in the blind current spectrum when non-uniform air gap exists. In literature, there is an approach called as MMF specific permeance analysis. So quickly recollecting.
Sir, I have one doubt. Sir, can you go back to the previous slide?
Yes.
Sarah asked me, like in between, like we may have some peaks also, like the magnitude versus frequency, like spectrum clear. So those lines are maybe having the substantial peak value. Right? So it's actually maybe the changes that whole should do by the time you are having that variation, like the three lines. Whereas one line you consider that maybe that's not required for us. But my question is that how do you know that that is not required? That maybe in between also having the lines.
Exactly. So that's the question. So the answer to that question is this component, right? Basically, I do not know whether this is accepted related or
Yes.
nobody knows. So we have to carry out an analysis. And that analysis is called as MMF specific permeance analysis. Okay, so that's what we are going to do now. It's all mathematical. So the goal is to make you write, derive equations, solve equations. Okay, and hopefully that will not let you sleep. So what is MMF? MMF, you know, is the product of flux and reluctance. Right? So we can write mathematically many forms. What is reluctance? Reluctance is length of the gap divided by permeability times area of the gap. And we also know reluctance is the inverse of permeance. Permeance is the inverse of reluctance. Permeance is the ability of the magnetic medium to allow flux lines to pass through. Whereas reluctance is the opposite. So in order to calculate flux, we need MMF and we need to divide by reluctance. density is flux per unit area. So if I divide the product of MMF and fermions per unit area, I get flux density. So what I am going to say is, I am going to call this as specific fermions. And this is MMF. So the flux density in the air gap can be easily synthesized if I know the MMF and the fermions associated with the system. So using this expression, let us try to get an expression for specific fermions. So fermions is mu air gap over length of the gap. Fermions by area, specific fermions. So I cancel this out. So what am I left with in specific fermions? P by A is nothing but mu by L gap. Right? Is everybody following? What is mu? Mu is a constant. So I can say that the specific fermions depends entirely upon the inverse of my air gap length. So this is an important relationship. Depends entirely upon 1 over the gap, which is nothing but inverse of air gap length. So is everyone in agreement with what I have said? So now we will try to do this analysis. So we know that if I can somehow model my air gap and its inverse as a function, and if the MMF for a machine is easy to express. MMF is ampere turns, right? So you know the turns, and if you know current, you can get ampere turns. It's not a big problem. So in MMF specific fermions analysis, what we will be doing is we will be looking at the MMF associated with the stator coils of a three-phase machine. This MMF, when interacting with the non-uniform distribution of air gap, will produce some flux density in the air gap. This flux density will induce currents in the stator coil itself, provided certain conditions happen. So that's the core of the problem. So the way things work is a little bit more complex than this, but the idea is you start with three-phase coil, you circulate current through it, it produces an MMF. The MMF along with the non-uniform air gap results in a fermion. So MMF times fermions per area gives flux density in the air gap. And this flux density will induce currents because it's time-changing flux density. It will induce currents in the same stator coil. And that is why we are seeing certain frequencies in the stator current. Okay. So this is the broad principle behind this MMF specific fermions analysis. So to answer the question, which frequency I should know as healthy or faulty, I should carry out MMF specific fermions analysis assuming my gap is uniform. I will get certain line frequencies. And then I will have to reanalyze assuming my gap is non-uniform. I may get same frequencies, I may get different frequencies. If I get different frequency spectrum, I know I can look for specifically 1 or 2 components in the frequency spectrum. Okay, so that's the idea. So first thing is the stator MMF. Now stator MMF, in electrical engineering we always start with a very typical assumption that the winding is sinusoidally distributed, right? But we know for a fact that it is not true. We cannot manufacture such a machine, or it becomes very intense to manufacture such a machine. So when we actually use a practical three-phase winding, stator winding, the winding distribution will result in what is known as space harmonics. How many of you have heard of space harmonics? Some of you have not. So basically, due to the spatial distribution of the three-phase winding, waveform will not be exactly sinusoidal. So instead of having a wave like this, we may have a wave like this. Okay? Step or staircase wave. And this staircase comes because we have to place only fixed number of conductors in different slots. If I do a harmonic analysis of this waveform, I will have a fundamental component which is of interest plus higher order harmonics. That higher order harmonics are called as space harmonics. Okay? That is because of the spatial distribution of the three phase waves. We also will have time harmonics later on when we use an inverter and inject time harmonic currents, but that is for another day. Now, to capture the MMF due to the winding distribution and the space harmonics associated with that, typically we can write a mathematical expression as given on the slide. If MMF in the stator winding is given as F subscript S, we get different order of harmonics. One corresponds to the fundamental frequency, 5 and 7 corresponds to higher order frequencies in the space harmonics. And we will see that usually a 5th order, 11th order will introduce backward rotating 3-phase vector. Okay, so what do I mean by that? If I take a 3-phase system, this is phase A, this is phase B, and this is phase C. If I consider this as positive sequence, if I multiply 5 times this, 5 times, let's say this is a magnitude and an angle 0. This is will be same magnitude but angle minus 120. This will be same magnitude, angle plus 120, right? If I do 5 times the angle, 5 times 0 is 0. 5 times minus 120. What is it? Minus 600. 5 times plus 120 plus 600. Okay. So in a circular frame of reference, when I have 360 degrees overall, plus 600 would be 600 is nothing but 360 plus some angle. 360 plus 240. So if I go around, this is 360 and then another 240 will be here. So you see here the phase C component, when it comes to 5th order harmonic, would be at negative 120 degrees with respect to its reference phase. Whereas phase B harmonic, when it comes to 5th order, would be at this orientation. So if you go, so minus 600 means you have to go clockwise, right? So you go 360 degree clockwise, then 360 degree 240 degree clockwise, you will end up here. Okay. So what we know for a fact is the space harmonics, certain orders would result in inverted phase sequence. So 5th order would result in inverted phase sequence. 7th order would result in same phase sequence as fundamental. 11th inverted phase sequence, 13th same, so on. So this is simple mathematics. You can do and check that. So therefore, to capture the space harmonics and its impact on the phase sequence associated with the fundamental component, we have to write the MMF expression as NP5 plus or minus omega t, where n is the order of the space harmonic, p is the pole pair number. What is pole pair? If a machine has 6 poles, the pole pair will be 3. So number of poles divided by 2. Okay. And this is the fundamental pole pair because higher order harmonics will have we'll see higher number of pole pairs. So that is the idea. Okay. And omega is the angular frequency or frequency expressed in radians, not in hertz. So 2 pi times f. And this is the supply frequency. Okay. And what is phi? So if you recollect the 2 circles that I have been drawing since morning, phi is the angular frame of reference on the stator side. So this is phi is the stator reference frame. In stator reference frame, an angular measure. Okay. I will also introduce expression where phi dash is the angular measure in the rotor reference frame and omega r is the frequency associated with rotational motion on the rotor side. Okay. So what is omega r? Slip is defined as in an induction motor omega minus omega r over omega. So omega r is 1 minus slip into omega. So this is my expression for MMF due to three-phase currents flowing in a three-phase distributed winding. So I have just written it. Actually, you can derive it by drawing the winding distribution, substituting current, and doing ampere terms like current times winding. And if you do the mathematics, you will get this concise form. That's right. I have just given you because we are only starting from MMF. Then we have to model permeance. Then we will go for it. So this is the first thing. The next thing is we have to model air gap. So this is a mixed eccentricity problem, right? So we are going to look at that. Thankfully, we are not going to model it all today because we have published literature available, so we can use that expression. But what I am going to do is I am going to show what happens when you have uniform air gap, how you can model it, and when you have some kind of fault, how you can model. So it goes step by step. Okay. So first let us consider, so our goal is we have to come up with a mathematical expression for permeance per unit area or at least permeance. So I need to come up with a mathematical expression for permeance so that I can multiply my MMF equation with the permeance equation and try to synthesize the frequency components in the flux density. Okay. So that's the goal. Okay. So you will understand when you complete this exercise. So let us begin with by assuming a healthy machine. So for a healthy machine, let the uniform gap between stator and rotor be G. Uniform gap between stator and rotor. What would be the permeance then? Permeance or specific permeance doesn't really matter to us right now, is a function of inverse air gap. So, right, it will depend upon permeance, will depend upon 1 over G. And since we are considering uniform gap, the gap is constant. It is irrespective of the position in the space in stator frame of reference, gap is constant. So P of phi is a constant which is given by 1 over the uniform gap between stator and rotor. Is this clear? I mean, if you are unsure, if you are unclear, please stop and ask. Don't hesitate. So I can easily represent this as, I am going to call this as a constant P naught. And the unit of this will be 1 over meters, right? It's the inverse of the gap. Gap is measured in meters, so 1 over meter will be the unit of this. And if you are looking at specific permeance, then you have to of course divide by area and get its unit accordingly. So this is P naught. So what is MMF specific permeance analysis say? If this is the expression for P naught, and the previous slide gave the expression for MMF, right? So MMF specific permeance says that I need to multiply my MMF with permeance. So let us do that. So MMF times permeance. So would be a flux or flux density, depends upon whether you are considering area or not. And we are looking at stator reference frame, right? So from stator's reference frame, this would be nothing but P naught into the MMF equation itself. P naught is a constant. So instead of writing the summation, I am just leaving it out. You have to keep that in mind that the summation always exists. So there is a constant Mn the stator frame of reference, commas NP phi plus or minus omega. So MMF into permeates. That's all here mathematically. And of course, this can will change depending upon the order of harmonic you are considering. Now, this is a flux from stator reference frame. I can consider the same flux from rotor reference frame. So, to represent the same flux from rotor reference frame, I need to replace my angle from the rotor reference frame perspective. So, what I will have to do is I will replace V naught cos NP phi is nothing but phi dash plus theta r or omega t plus or minus omega t. Right? So from the rotor reference frame, I have replaced my phi with the equation phi dash plus omega r. NP phi dash plus NP omega RT plus or minus omega. So once this flux or flux density exists in that air gap, we are looking at this flux density from rotor reference frame. This is how mathematically we are representing it. This flux density will have a frequency and it's a function of time, right? So that means the flux density or flux is time changing in nature. Now imagine an induction motor, there are rotor bars. The rotor bars are exposed to this time changing flux. Any conductor that is linked to time changing flux and EMF will be induced, and because rotor bars of an induction motor are short circuited due to end rings, the EMF will result in current flowing in the rotor, right? So whenever current flows through a conductor, there is ampere and there is turn. Therefore, it's ampere turn. That means another MMF is being produced due to current in the rotor. So, due to current in the rotor, another MMF is produced. Let's say and that current might be lagging this flux by some angle, right? Typically, lagging or leading. It will be at a different angle. It may not be in phase. Even if it has to be in phase, let it be. We can indicate it by introducing an angular measure. I am introducing an arbitrary angle to say that the current flowing can be at any angle with respect to the flux that induced it. It need not be in phase with that flux. That's all I am doing. Now this MMF, if you look at it from the stator reference frame, how will it look like mathematically? So we have to again replace this using the angle associated with stator frame of reference. So the MMF, due to current flowing in the rotor windings, can be so basically this MMF will interact with the air gap. The MMF interacts with the permeance, right? Permeance. So this MMF into permeance. So another flux will be introduced in the air gap So this MMF due to current flowing in the rotor interacts with the air gap and produces another flux in the air gap, which is nothing but MMF times permeance. That is given by this expression. So it's a two-way process. You start from stator MMF produces flux induces current in the rotor. Once current flows in the rotor, it produces its own MMF. This MMF interacts with the air gap and produces a flux density. And that flux density is what we have written. Flux is what I have written. Now I can look at this flux from stator frame of reference. Right? So this is the air gap flux due to current flowing in the rotor. This I can look at it from the stator frame of reference. So if I reconvert this variable into stator frame of reference, it will become NP into phi plus or minus omega t minus theta. Right? So this is how the equation will look like. Am I correct? So this is in the stator frame of reference. So do you understand the flow? You start from stator, multiply with the permeance function, get the flux density, introduce currents in the rotor, then rotor MMF will again interact with the same air gap, will introduce its own flux components, and that when looked at from stator reference frame will be like this. Now this flux density is also time changing in nature, can induce currents in the stator windings. It can induce currents in the stator windings provided the condition for this flux to induce currents in the stator winding is the pole pair numbers. So basically the number here, NP, or this pole pair number has to match with the main pole pair number. So the main stator MMF pole pair number and the air gap flux densities pole pair number have to match. If they match, currents will be induced, and the frequency of such currents are given by this omega. And as per this equation, because the pole pairs match, right? NP is same as NP in the other equation, right? Currents will be induced, and what will be the induced currents? The frequency will be omega, which is nothing but supply frequency. So that means whatever was the supply frequency, the same current is what we expect. And because of the space harmonic, we will see first, fifth, seventh like that. Okay. So this is the basic idea of a uniform air gap machine. The approach is the approach here. So we start from stator MMF, model air gap or permeance, multiply them to get flux in the air gap. That flux will induce currents in the rotor, which will produce rotor MMF. The rotor MMF will again interact with the air gap permeance, produce flux. This flux can induce currents in the stator provided pole pairs of the flux in the air gap and the MMF of the stator winding match.
So then call that different frequency as a harmonics, because we have seen whatever the purpose we have taken, that is appearing in different frequencies.
Exactly.
But here we are relating to the supply frequency.
So this is under healthy condition. So
First assumption you made is.
this is under normal condition. So under normal condition, we expect only supply frequency. That's all we are saying. Now we have to go for a faulty condition. Okay? So our first goal is, let us consider one fault. Let's say static eccentric fault. To keep things simple, I will take some measures, numbers. Rather than generalizing, I will give some numbers. Let us say the machine has a uniform, initially when it was healthy, has a gap under healthy condition. Okay? Under healthy condition, gap is 10 mm. sake of ease of mathematics, we are using 10. Okay. Whenever there is a static eccentricity, what is happening? The center of stator is offset from the center of rotation, right? That is the basic definition of static eccentricity. We have an oval stator. The rotor is rotating about its own axis. And the distance by which the minimum air gap happens. So, static eccentricity results in minimum gap of 5 mm. So what do I mean by that? So this distance is 5 mm. Initially the distance was 10 mm. Now the stator's center has got offset in such a way that the distance has reduced on one side to be 5 mm. So what would be the distance of the other end? 10 plus 5, right? 15 mm. So the minimum gap has now become 5 mm. Gap in meters or millimeters. Healthy condition. Healthy condition was flat 10 mm. Right? Is everybody agree? Healthy condition is straight line. 10 mm. When I have 5 mm minimum distance and a static eccentric fault, how will be my air gap variation along the angle? So the minimum will be 5 mm, maximum will be 15. Plot it. So this is 90, 180, 270, 360 degrees. Do you agree? So this is the gap under faulty condition, under static eccentricity. I am going to call that as SE, static eccentricity. So we are just one step away from you starting to work. So what I am going to do is, I am going to write a mathematical expression and I am asking you to verify whether you get this function. Okay? So I am going to say, the literature published says, static eccentricity fault can be mathematically represented. So the gap under static eccentricity gap under static eccentricity is gap under healthy condition minus the minimum gap times cosine of the angular frame of reference phi from stator frame. Angle phi from stator frame of reference. So this is the mathematical expression. So let me write it on the next slide just for clarity. So published work states that healthy minus the phi is the angle from the stator frame of reference. Okay. So I am going to give you a few minutes. I want you to check whether this mathematical equation actually corresponds to the function that we have drawn. So I am going to give you a few minutes. Check that. This is your time. You have 2 minutes time. Let's say I have given an expression. You know what is the Eventually, I realized that lab is a better place because you can put your notebook somewhere and write. Seminar have note tables. Anybody could verify? So you substitute different angles for phi and check. So GH is 10 mm, G min is 5 mm. So if we extrapolate with phi versus G static eccentricity, when phi in degree is 0, what is cos 0? 1. So 10 minus 5 into 1, which is 5, will give me 5 mm. What is 90 degree value? 10 mm, right? 180 degree will be 15. 270 will be 10 mm. 360 same as 0. So essentially this mathematical expression given in literature is validated. So we can be safe. We can be confident that yes, whatever we say is correct. So this is the mathematical expression for this function air gap under static eccentricity versus angle in degrees. 15 is 5 into. So for our analysis, we don't need expression for air gap or gap. What we need is permeance. And we know that permeance depends upon inverse of air gap. Right? So permeance under static eccentricity will be 1 over, or depends upon 1 over gap under static eccentricity. So that is 1 over G healthy minus G min into cos phi. Right? Now let us look at from a practical perspective. Rather than writing like this, what I am going to do is I am going to divide the denominator by GH completely, the healthy air gap. So I am going to say that this function is same as 1 over 1 minus G min over GH times cos phi. Do you all agree? What is the, okay, now let us look at boundary conditions. When there is no static eccentricity, what is the value of G min? When there is no static eccentricity, what is the minimum air gap you can have? So this G min is the point, right? So when there is no static eccentricity, then G min vanishes. Right? So that means this becomes 0. If this is 0, then only we can say that there is no eccentricity for it. Right? So under healthy condition, G min is 0. The worst case, what is the maximum value G min can take? How far can the center be offset? The worst case value for G min would be GH, same as GH. So I can say that G min theoretically should lie between this distance, right? So what I can conclude is this ratio G min over GH should lie between 0 and 1. I am going to call this ratio as severity of static eccentricity. You can express it in percentage. So in the example values I have chosen, when we have 5 mm minimum gap for a 10 mm uniform gap machine, the severity is 50%. 50% is very high. When the severity percentage is less than 10, it's very small. When it is above 10, we are entering faulty condition and we have to diagnose it. 50% is huge that we have to immediately stop the motor and diagnose it, fix it. Okay. this expression becomes 1 over 1 minus severity of static eccentricity Gaussian. So this is the expression for our permeance function, right? This is the expression for our permeance function. Now what I am going to do is I am going to let you substitute different values of angle. You know ES in this example is 0.5. So here it is 50%. Substitute different values of phi and create a table for different values of phi. What is the permeance function? So at 0 degree, what is the permeance function value? Sorry?
I think the formula is wrong. So instead of GIAN, we should keep we should not keep GIAN. It won't work. Instead of GIAN, we should be distance between the centers. Can you go back?
Okay. So G min can also be considered as the distance between the centers.
It should be distance between the centers. I mean, if you take instead of 5 mm, if you take 3 mm as GIAN nodes, the distance between the centers will be 2 mm. It will come 10 minutes to cost, I not 10 minutes to cost.
So if I, so you are saying that it should not be G min, but
It should be distance.
distance between the centers to for this. How do I choose a wrong value of phi? Because it's symmetrically looked at. So you are essentially saying that if the centers C1 and C2 are offset by some distance, it makes sense. So that is G min. We can consider that as the G min here, but that's the distance between centers. Thank you for staying there. So everywhere I have changed it. So essentially it is the offset from the original state of the centered or aligned condition, right? So it should be measuring from the centers makes more sense. So if I have two circles, the same center initially, and then in the second case, if the center of one circle is offset by a distance, okay, so please substitute and tell me the values, please.
Shall I use the
One, 180 degree, 0.67, So what I'm going to do is I'm going to plot this function and give you degrees.
Hello.
Versus fermions. You start at 2, goes down to 1. Check.
I feel like I'm piloting. Anyways, thank you. So the angle when it is 0, I have a peak value, and when it is at 180 degree, I have a minimum value at 360 degrees, going back to the original. The reason why I'm not bothered about the values at this point is I just wanted to look at the function and tell me what mathematical function it resembles. Sine, cosine function, right? It's a shifted cosine. So what I can say is I can generalize my static eccentricity air gap as a constant air gap, constant P naught plus some P1 times cosine of phi. So this is how we will have to synthesize the permeance expressions for different fault conditions. Okay, is this clear? So this is how we have to model the permeance expression for different fault conditions. So static eccentricity in isolation is not useful. The most common form is mixed eccentricity. I am not going to go into the details, but based on literature we know that the mixed eccentricity permeance function can be approximated to this general form P1 cos phi plus P2 cos phi minus theta r, where theta r is omega rt. Theta r is omega rt and phi dash is phi minus theta r. So this is from literature. I am just taking the expression and I am giving you. You are welcome to read a few papers and actually mathematically derive this for dynamic eccentricity and combine it for mixed and see what happens. So what I am trying to say is, so the mixed eccentricity air gap, its inverse when we model, which will give us the permeance, will be of this general form or can be approximated to this general form. Why did we do all these things? Because we are interested in doing what is known as an MMF permeance analysis. Right? MMF permeance analysis demands an expression for permeance function. Therefore, we have to come up with this expression. So once we have got this, my MMF in the stator winding is MNS cos NP phi plus or minus omega t. Right? Do you all agree? This is the expression I wrote or I showed on slide. So what I am going to do is I am going to make mathematical multiplication, MMF times permeance. For the sake of time constraints, we won't do the entire multiplication because that will lead to too many terms and too long an activity. What I want you to do as a first step is just consider P1 cos phi, the static eccentricity component of permeance function, multiply it with this. So let us try to do it together. So the flux produced in the air gap due to the MMF interacting with only the static eccentric component of the permeance function. Again, this is in stator reference reference frame. So that will be MNS P1 cos NP phi plus or minus omega t cos phi. What is the function cos A cos B? Trigonometric identity. Anybody remembers? Cos A cos B. Cos A.
2 into cos of A plus B.
Cos A plus B by 2.
Cos A minus B plus cos A by 2.
Okay, so we have cos A cos B as cos of A plus B by 2
Cos of A
plus cos of A minus B by 2, right? So we have two terms for this product. So the flux produced in the air gap due to MMF interacting with only the static eccentricity permeance function will have two terms. So I'll give you a moment. So try to solve for that and write me the expression. So let us get the expression. That will be MNS P1 by 2 cos, the phi terms get added, NP plus 1 phi plus or minus omega t. This will be one term plus MNS P1 by 2 cos NP minus 1 phi plus or minus omega t. Is this okay? So I have cos A cos B. So the phi terms will get added and subtracted. NP plus 1 phi and NP minus 1 phi. There will be two terms. So this is all from the stator frame of reference, right? So we have to now look at the same flux density from rotor frame of reference. So the same flux density from rotor frame of reference would be NP plus 1 phi is phi dash plus omega t plus or minus omega t plus P1 by 2 cos NP minus 1 phi dash plus omega t plus or minus omega t. So the same flux density, when we look at it from the rotor frame of reference, will be represented like this. Any questions at this point? We haven't done anything extraordinary. We are just multiplying the permeance, one component of the permeance function with MMF. We are expressing it mathematically. So this flux density will interact with the rotor conductors, will induce current in the rotor bar. Once current flows in the rotor bar, there is a rotor MMF. That rotor MMF will again interact with air gap flux density, right? So then the rotor MMF is interacting just for the sake of interest or interesting sake. Let us assume that it is, I think I missed cosine function here. Sorry. P2 cos phi minus theta. Please fix this. That must be a cosine function. It's not P2 into phi minus theta. P2 cos phi minus theta. This is corresponding to dynamic eccentricity. This is corresponding to static eccentricity. This is LT. Okay, there will be three terms, one corresponding to static, one corresponding to dynamic, one corresponding to LT. So what I am going to say is, this MMF, when interacting with the air gap permeance again it has to interact with the entire function, but for the sake of time and for interest's sake, let us assume that we are looking at the interaction between the dynamic eccentricity component and the air gap flux density. Okay. So let us multiply this permeance function with the MMF associated with the So I have to take this and then multiply it with phi minus theta r. What is phi minus theta r? It's phi dash, right? So I can say that minus p1 by 2 cos np plus 1 phi dash plus omega t plus or minus omega t plus multiply it with p2 cos phi dash. This is the dynamic eccentric term, right? p2 cos phi dash. Is that okay? So likewise I will have another term mns p1 by 2 cos np minus 1 phi dash plus omega t plus or minus omega t into p2 cos phi dash. Right? So each term will result in two terms because they are product form. So when you expand it, you will get two terms. So we will essentially get four components. Let us consider just the first one for the sake of analysis in this workshop and let us explore it. I hope everybody is able to follow so far. We are doing the same approach as we did for healthy condition. Now that we have considered a mixed eccentric condition and we are picking and choosing like certain functions, you can do the entire analysis and you will get the same thing, but this is an easy way to check. Okay. So let us consider the first term. So let us just consider this one and let's see what happens. So if I multiply them, it's cos A cos B. So cos of A plus B by 2 plus cos of A minus B by 2. So what I will have is minus P1 P2 by 4 cos NP plus 1 phi dash plus phi dash plus NP plus 1 omega t plus or minus omega t. So I hope you are able to get this. So NP plus 1 phi dash plus phi dash. Do you agree? So multiplying this term, so NP plus 1 phi dash plus phi dash, NP plus 1 into omega plus or minus omega t. So this is cos of A plus B by 2 plus I will have minus P1 P2 by 4 cos A minus B. So NP plus 1 phi dash minus phi dash plus NP plus 1 omega t plus or minus omega t. So I can simplify these two expressions. So I am just focusing on these two. So I am simplifying these two expressions. So this will result in NP plus 2 phi dash, whereas this will result in NP phi dash. Okay? Any questions? So let us now rewrite this expression after simplification. So after simplification, this will be m minus p1 p2 by 4 cos np plus 2 phi dash plus np plus 1 omega t plus or minus omega t plus p1 p2 by 4 cos np phi dash plus np plus 1 So these are all flux components from rotor frame of reference, right? Because we are looking at angle phi dash. The same flux, if we look at it from stator frame of reference, this expression can be rewritten in this form. So in stator frame of reference, to be MNS P1 P2 by 4 cos NP plus 2 phi dash is phi minus omega t plus NP plus 1 omega t plus or minus omega t plus MNS P1 P2 by 4 cos NP into phi minus omega t plus NP plus 1 omega t plus or minus omega t. In case you have any questions, doubts, do not hesitate to ask. So let us simplify this. So I have omega t term here as well as here. I have omega t term here as well as here. So np plus 2 times phi minus np plus 2 times omega t plus np plus 1 omega t. So what will that result in? Minus omega t. Right? Do you agree? So this entire term can be rewritten like this: np plus 2 times phi minus omega t. If you simplify, np plus 2 into phi, np plus 2 into minus omega t, and then here I have np plus 1 into omega t. So np omega t will cancel each other. Minus 2 omega t plus 1 omega t will become minus omega t. Likewise, I can simplify the lower term, and this will be np phi minus or plus omega t. So we never thought life would get this complicated when we started. But this is only a small part of that long expression, right? So your homework, you know already what your homework is today.
So this is the omega t, right?
Omega RT. No, no. This is the numerator. This is the first term. This is another term. So let me rewrite this on next slide using simplified form. So my flux in the stator reference frame would be MNS P1 P2 by 4 cos NP plus 2 phi minus omega t plus or minus omega t plus MNS P1 P2 by 4 cos NP phi minus plus omega t plus or minus omega t. Right? So this flux in the air gap can induce currents in the stator windings provided the pole pair numbers of this function matches with that of pole pair number of the original stator MMF. What is the original stator MMF? We have to go back quite a few slides to even know where we started. Problem mistakes on that. So here is the original they match, what do we mean by that? N is equal to 1, 5, 7, 11, 13, like that. P is equal to pole pair, right? So if the 4-pole machine, P will be 2. Right? So NP would be the product of these two. So for any given machine, P cannot continuously change, it is one value. So P times N is a product. Right? NP plus 2 means, so let's consider N is equal to 1, it will be 2 plus 2, 4. N is equal to 5, it will be 10 plus 2, 12. In the original function, we had just NP. So can NP plus 2 ever be equal to NP? In this case, you have to check. Okay. So for example, what I am trying to say is, you can take a higher order NP from the MMF function and you can compare with NP plus 2. So if the orders match somehow, then currents can be induced. If the pole pair numbers never match, then current cannot be induced. So what you will realize is this term will not induce any current. But you look at the other term, this matches. So current can be induced. So what will be the order of frequency? It is omega t plus or minus omega t is there. Omega r plus or minus omega times t. Right? So there is an additional frequency component that corresponds to rotor frequency that is showing up in the line current due to mixed eccentricity fault. So this is the analysis you will carry out for different faults, and remember that we have just taken one term initially in one direction and one term in the other direction. When we went from stator to rotor, we started with static eccentricity Tomian's function only, and we went back from rotor to stator, we just chose dynamic eccentricity function only. If you use all of them, you can see what is the impact. Invariably, you will see based on literature, what we know is we will have omega plus omega r and omega minus omega r, where omega is supply frequency and omega r are the rotor frequency, so sideband. So we will say, we call this as sideband elements. Sideband frequencies or sideband. So just about the fundamental. So if this is the 60 Hz or 50 Hz component, so this is 50 Hz, you will see one here, another one here, another one here. So these are sideband components. Okay? Sideband means something close to the fundamental frequency. So mixed eccentricity fault in motor current signature analysis is typically diagnosed by looking for this plus and minus omega r terms around the fundamental frequency or the sideband frequencies. So the moral or the summary of this long exercise is, if we have to carry out current signature analysis to diagnose mixed eccentricity, we have to do the spectrum or current spectrum or frequency spectrum and look for around the 50 Hz of fundamental frequency. We have to look for sideband components. So depending upon the rotor speed, it will be offset. Okay. So that is how you can estimate. So this is all fine for an induction motor, right? We started with uniform air gap machine and everything. Now what is happening with electric vehicles is, what is happening with electric vehicles is, the machine is inherently, if you take a high-speed electric vehicle motor, you will have interior permanent magnet machines, or you will have salient rotor structure. Okay? So interior permanent magnet machine will result in air gap saliency. That means gap. In some of the portions it's shorter gap. So all this exercise that we did are considering the air gap is uniform under healthy condition. When we have to accommodate saliency, modeling becomes more challenging. So if you have a square gap under healthy condition rather than a steady line, so this square waveform indicates a salient port structures air gap under normal conditions without any fault. So that will, if you look at it from three-dimensional perspective, stator angle, rotor angle, this is how it will look like. So when you do the eccentric fault, the air gap can be thought of as a function of stator angle or rotor angle. It will be very different. So we have to come up with an inverse function. An inverse function using traditional approaches have some drawback when it comes to modeling a salient pole machine, which is quite common in electric vehicles. So the traditional way of modeling inverse air gap has found to be inadequate, and we had to come up with a newer method of modeling this inverse air gap. And this newer method of modeling gives us the inverse air gap function at a mixed eccentricity fault to be a function like this. Some constant times cos L phi plus or minus m theta r, where L is a number that varies from 0 to infinity, m is a number that varies from 0 to infinity. So it's an extensive harmonic order. So you have to approximate it at some point, right? So essentially that's the idea. Okay. So you will see that this is how we have to take inverse air gap function, and then we have to carry out MMF specific permeance analysis, and when we do it for salient rotor structures, different fault frequencies are
We have a breaks.
and finishing. So this can be visualized. So healthy condition results in certain frequencies, static, dynamic, mixed.
So, then what is the GIAN set?
Healthy. I just for consistency, root HE rather than H. So HE means healthy. Okay. So we can see the frequency spectrum like that. So this is how we have to theoretically expect what fault would introduce what components. So this, let us stop here, and then after a break we will come back and get started with the software. Thank you. Quite easy. In fact, modeling is a big research domain. If anybody is interested in condition monitoring, you should consider modeling as your one of your areas. So just creating real-time models. So if you have access to a real-time simulator, creating a real-time model of the motor which can accommodate such fault and run in real time it will get you at least one PhD, if not more. There are lots of opportunities. So what is coupled circuit model? It's a very simple standard structure. You have your stator voltages, 3-phase voltages or line-to-line voltages. Typically these are all phasor, so phase voltages. You have stator resistance, 3-phase, and this is going to be a matrix. And then stator phase currents plus the rate of change of flux linkages associated with stator. Right? And lambda is nothing but LSS IS plus LSR IR, where LS is the self-inductance matrix and LSR is the mutual inductance matrix. When you have a 3-phase system, you have LAB, LAC, LBC like that. Right? And for the rotor circuit, because we are looking at induction motor, we can model the rotor bar as a circuit. Okay, so, and we can write equations. And because the rotor windings are So these are the voltage expressions. The torque acting on the motor shaft is given by load torque plus inertia component, like acceleration or deceleration torque. And we can use co-energy, rate of change of co-energy for computing torque. So it's d by d theta or dou by dou theta of 1/2. Usually half Li square typically is what we will use, but because this is matrix, we may have to use appropriate dimensions. That's why we have IS transpose LSS IS plus IR transpose LR IR plus mutual inductance series. Okay. So these equations themselves are very standard. Whether you want to model motor for eccentricity or normal conditions, these are standard equations. But what really happens is when we have air gap non-uniformity, if you recollect your morning session, we wrote expression for inductances, right? Inductance is n square over reluctance. Reluctance depends upon air gap. Now air gap is no longer a constant. That means your inductance will no longer be a constant. Inductance will be a function of theta. So in this expression, torque expression, each of the terms, inductances are functions of theta. So as rotor position changes, the inductances of each of the windings at different rotor positions are varying. Okay. So calculating these inductances is one of the most time-consuming job in this approach. And in order to calculate inductance, a specific type of approach is reported in literature. It's called as a modified winding function approach. It's a very advanced topic. We are not bothered about it. The main reason is the other approach of modeling, which is finite element based, is much simpler when it comes to modeling. So we are not too bothered about modified winding function approach. So I won't go into the details. I want you to be aware that it is possible to model inductances which are function of rotor position using the reported technique in literature called as winding function approach or modified winding function approach. The idea is very simple. If you consider a stator as shown here with just two conductors, as you go around the stator in one direction, let's say in counterclockwise direction, the turns function includes the total number of turns. Okay, so if you have a conductor arrangement like this, if current is flowing inside or into the page on this conductor, then it has to come out of the page on this conductor, right? So the direction of current vector is also taken into account in sketching the turns function. So what I'm trying to say is, as you go in here, it's like using Ampere's law. So the net ampere turns enclosed in this path would be, if n number of conductors are here, then it will become plus n at this position. As you go around, you have to, because the direction of current has reversed, you have to subtract. So it will become minus n, plus n minus n becomes 0. So this type of drawing, where you sketch the winding distribution and the conductors and the current flowing through it, using the direction of current flowing through it, is called as turns function. Okay? And then the winding function would be subtracting the turns function. So this is for a three-phase stator, which has multiple slots and multiple conductors. So you can sketch the three-phase turns function. Okay? And then you can calculate inductance using this expression, where NA and B are the turns function, G inverse is the air gap inverse function, and these are average values of the turns function. So this is again a sophisticated approach. We won't bother about it too much at this point. I want you to be aware that there is a mathematical technique called as modified winding function approach that will allow you to compute inductances that are rotor position dependent. Okay? And you can see the inductances for different faults. So under healthy condition, the inductance is given here. Under static eccentricity condition, the inductance changes. So inductance as a function of rotor position. So this is the mutual inductance between stator and rotor. So So stator face A and a particular rotor bar, as you rotate the rotor, will be of this shape under healthy condition. When you have a static eccentricity, the inductance itself will change like this for one rotation. So face A to a particular rotor bar. For dynamic eccentric condition, the inductance will be same in shape as static eccentricity, but the magnitudes will be altered. And for mixed eccentricity condition, it will be a combination of static and dynamic, right? So it's going to be something like this. So this is how you will synthesize inductance. And these are the stator self-inductances, or basically LAA, LAB, LBC. So basically, these are mutual inductances of the stator windings, LAB, LAC, and LBC, under healthy condition and a mixed eccentric condition. So they are completely position different. So you can use them to simulate. But this approach is very sophisticated, mathematically intensive, and therefore it's not as popular now as it was a few years ago. So now the most popular technique is what is called as finite element simulation. So in this lab, you have access to a particular software. So this is a commercial software. You may or may not have access to this from your institution. If you don't have, you can look for some free software tools that may give you similar capabilities. Okay. But commercial software will come with its own advantage. So what I'm going to show you is quickly how you can model a motor, let's say, and then you can go into modeling eccentricity fault, right? So if you open a commercial tool like this is called as ANSYS, and the software is electronics desktop. We are using a student version for the purposes of this workshop, but you can buy a license. So the easiest thing is to open an example. This software is very powerful. You can do lots of simulation with it, lots of different types of simulations with it. I'm not going to talk about the software, that is not my intention. I'm just going to focus on how easy it would be to model the machine. So let us open an example. And since we have been talking about induction motors, let's get started with the induction motor. When you click on open examples, it will give different types of tools within the software. We will go into what is called as an RMXPRT tool. It's a library basically. It allows you to quickly model motors. This has multiple examples. I'm going to take induction motor IND-M3, let's say, just a random. And I'm just choosing YZ206 as an example. You can choose any example, I'm just choosing one example. The first thing I will do is I will save this because it's an example file. I don't want to corrupt it, so I will save this on the desktop. Okay, I have saved it on my desktop, so it's a copy of my example file. So you see here this example file has stator, rotor, everything. So you can easily expand it, and you can go double click on the machine, and it says 3-phase induction motor, 6-pole machine. These are the details that are given by default. And if you expand this machine, it says there is stator, there is rotor, and shaft. So stator, if I double click, it says this is my outer diameter, this is my inner diameter, this is my length of the shaft, the length of my stator, etc. Stacking factor, steel type, number of slots, slot type, so many details are there. So the good thing about this library is I can edit and see what happens. For example, right now there are 72 slots. It's a 6-pole machine. Typically, number of slots per pole should be an integral number. So 72 should be a multiple of 6. Let us choose another multiple of 6. Rather than 72, let's say I use 36. So I will give 36 slots. I give OK, you see already it visually updates. So then it becomes easy for you to play around with it. Sorry. Play around with it. So you can go back. Now you will diameter. That means the core will get saturated. select material. You can say steel or whatever material you want to choose. Most of the other parameters, for example, stacking factor, you will not know. You will just use the default values. You can change around a little bit, but you don't have to bother too much. If you expand stator, there is slot specific information you can enter. For the selected slot type, what are the dimensions? The winding type, is it single layer or double layer? Number of conductors per slot? Number of strands in each conductor? What is the wire size? Diameter. So all those details you can give. Again, if you don't know many of these, you can leave them to default and you can work with it. Okay? Rotor, if you double click, it says number of slots is 58. Outer diameter of the rotor is 209.2 mm. So if you recollect the default value of inner diameter of stator, it was 210. So the difference between the two will give you air gap, which is like less than 1 mm, right? 0.8 mm. So the concentric gap would be just difference in the diameters. It will not be difference by 2, just will be the difference. So if you just draw two circles, the difference in the diameters will give you the gap. And length will be fixed. In the diameter is all those. In the student version, there is a bug. So if you go into rotor window and if you click on the material type of the steel, then software will crash. So don't do that. It's just a bug in the student version of this 2024 release.
Latest is 2024.
Just in 2024 release they have this bug. So when they release the next version, they will fix it. I mean, the reason why I'm saying that is otherwise people have built it from scratch, but anyways. So likewise you can change the slot and winding for the rotor too. And in the induction motor, the winding is like there's just a cage, right? So you can decide the cage, aluminum type, number of like what is the height of the end ring, what is the width, what is the end ring conductor, etc. And then shaft diameter you can specify whether you want to have a magnetic shaft or a non-magnetic shaft can also be selected. So usually you will not have a magnetic shaft, you will just have straight flux along there. And then you can go into the analysis and you can set up, you can say what is the rated output power, what is the rated voltage, rated speed, rated operating temperature. And you can enter these details. These are available from mainframe. So you should know them for any motor. And then what you will do is you will right click and you will say analyze. And you will do some analysis, it will give you a message. So until now there is nothing fun. So you are using a model and you can enter parameters, you can change the dimensions and say. But after this comes the biggest advantage. So what we really want to do in our analysis is we want to have a setup where we have a motor model which can be excited from an AC source or an inverter. The motor must spin connected to a load and the current calculated at different instance must be available to us as a measured data, right? That's the goal of our, because we want to do motor current signature analysis, right? So we want to run the motor excited from a supply. When if the motor is loaded, it will draw current. I am interested in that current waveform, time domain current waveform. Right? That is the goal. In order to carry out such a simulation, this software has what is known as transient simulation tool. And the good thing is, if you have a full version, you can carry out transient simulation easily. So by right clicking on the setup, once you have analyzed, you will get an option called Create Maxwell Design. And if I click on it, it will take me to analysis. 2D design is fine because we are looking for static and dynamic. If you want to do inclined eccentricity analysis, you remember inclined eccentricity is along the shaft there is still tilt. Right? Then you have to generate 3D design. Now just looking nicety perspective and generating a 3D model and clicking OK. And then in a few minutes, the software will generate a 3D motor model for you. So it will generate a cage, winding, so it's creating 3-phase windings. So your modeling of your motor becomes very easy if you have some basic dimensions. Then you can use an example model, you can play around with it. You can change the gap, you can change the slots, you can change the conductor arrangement, and you can generate a model on which you can carry out transient analysis. When we do this step, when we go from RNX PRT model and say create Maxwell design, the default simulation that the software expects us to do is transient simulation, which is what we want to do. Basically, we want to run the model at different time instance and see what is the current, what is the magnetic flux density, etc. Because this is a 3D model, it generates a lot of, it takes some time, it takes a few minutes, and it is trying to generate different elements. If I had selected 2D design, it would have generated the model in 2D view and it would be much quicker. The drawback of the student version is once we are in transient domain, we cannot do any simulation because we don't have the license in student version. But in full version, we will have the license. So the default setting of this model, of this software is such that it will generate a full model first and then it will analyze. If it is axis symmetric, then it will take only a section of the model and it will place. Because that is symmetric model, so it is just using 1.5. That is good enough to analyze. We don't need the complete model is what I'm saying. So rather than this, what I am interested in is a complete model. So what I have to do is, rather than using the PD half part, I want to do a complete model. So to do a complete model, I need to go into the RNX PRT model, right click, and if I click on design settings, so this is an important part. And if you go into user defined data, enable it, and you type fractions is unity, and then if you reanalyze, and then you can basically create Maxwell design again. This time let's do 2D design so that it is quicker, and you will see that you will get the complete motor model. The example I chose was not a good one. So it is able to generate 3D model because of the basic dimensions. I changed some values, right? So probably made some mistake. It's not a proper value. It's showing some error. So let's wait for one or 2 minutes. Once the model is completely generated, I will show you the transient mode, and then you are free to work on the model like software as it is. transient domain, what we really want is if you expand it in the transient domain, the most important features are only two things. So one is what is called the motion setup. In motion setup, if you double click, you have to, the motion setup has to enclose all the rotating parts of the motor. So in this case, it will be the rotor along with the bars and when here. And once you go into the motion setup, you click on mechanical, then you can say consider mechanical transient, and you can select what is the initial angular speed. You can set it to 0 if you really want to start up. Say if you are studying startup sequence, you set it to 0. If you are interested in steady state behavior, set it to a speed close to steady state because you can minimize the simulation time. Okay. What is the moment of inertia of the system along with the load? What is the damping constant? You can also give a load torque. It can be a constant value, or you can say until the particular speed the load torque is a particular value, and beyond that speed the load torque changes. Or you can also express load torque as a function of time. If time less than 0.2 second, load torque be 0, else load torque be full load, right? Whatever the value is. Then it will apply load accordingly. So you can do different things. So this is one important parameter. The other thing is excitations. So in excitation, you will have three phases. So phase A, you can select what type of excitation you want, whether you want to give current excitation or voltage excitation or an excitation from an external circuit. So if you want to have an inverter driven machine, you will set this to external excitation and you will have to model the inverter. Okay. But typically if you have just a voltage excitation, that is more traditional, and then you will give what is the resistance of the coil per phase resistance, and then you will define the supply voltage. So peak value of the supply voltage times sine 2 pi of t for phase A. For phase B, everything will remain same except there is a phase shift, and phase C another phase shift. Okay. So these are the two things that you will modify. Once that is done, you will go into analysis, and you can right click or you can just open the setup, and you can say how long you want to simulate for, and at what time step you want to simulate the system. Right? So if you really want final time step, it's going to take longer time. If you want to simulate for longer duration, it will take longer time. Almost takes. So if you are doing a simulation of a 50 Hz system, in order to get a good looking sine wave, you want at least 20 to 30 data points. Right? So 50 Hz in time domain would be 1 over 20 milliseconds. So you want to do at least 20 points. So 1 millisecond should be the minimum time step for 50 Hz. 2 milliseconds again 25 data points. 10 data points. So maybe 0.5 milliseconds or 1 millisecond will give you a good resolution. But then you are going to extend your simulation time. Right? So this is what. And the good thing is in this, you can also save magnetic field information at different instants in time. And you can create, you can say that save every 0.3 seconds or 0.2 seconds like that. Or you can create a table and you can say at different rotor positions to save the magnetic field. So that at the end of the simulation you can also visualize how magnetic field has changed. So with this approach you can model the machine quite easily. I'll close this and open up a 2D model because I badly need a 2D model to show you how you can introduce eccentricity, right? So by definition, as Nirunandan pointed out, we are going to offset the centers and see. So that is what we really want. I can even look at it here. So just zoom in. So this is a better view for me to let's forget this moving for a moment. Let's look at the machine itself. So the air gap is the measure between here and here is my air gap. So that gives to be 2.9 mm for the values we can set. Right? So between the rotor tooth and stator tooth, whatever is the distance, that is my air gap. Do you all agree? Is it clear? 2.9 mm is the distance. So go on to measure, select a starting point, position, and then you go into that. So from one side, rotor tooth to stator tooth, whatever is the distance is there. So 2.9 mm is the distance in the healthy case. So if you want to introduce 50% eccentricity, static eccentricity, you will select the stator. So if you want static eccentricity, you select the stator and offset it in one direction, opposite direction. If you want dynamic eccentricity, select the rotor and offset it by some distance in one direction. And if you want mixed eccentricity, you have to move both a little bit in one direction. Right? So that is how we will do it. And when you do that, because of the software setting, we may have to delete this moving circle first, move everything and redraw a moving block and do the simulation. Otherwise, you will see encounter an error in this software. But what I'm trying to say here is, it wouldn't take you, to learn the software itself, it will take you some time. But once you have acquainted yourself with the software, there are so many video tutorials nowadays from the supplier. You can also find on YouTube there are different individuals doing tutorials. But once you have acquainted yourself with the software, modeling a motor and introducing eccentricity fault is going to be way easier than the other approach of modeling a motor using coupled circuits and introducing eccentricity fault mathematically. Okay. So that is the big benefit of finite element simulation. So the main idea of the workshop was to show you, but there's not much time left for the day. But what I want you all to acquaint with the software. So what I would recommend is, don't start with this all these things. When you want to get started, the best way is go into help, Maxwell PDFs. Then there is Maxwell Getting Started Guide. What I would suggest is start with something called as magnetostatic problem. Magnetostatic problem means you are going to give DC current into the coil and see how flux is going to be distributed in that environment. That is what we call as a magnetostatic problem. That is not a problem of interest to us, but that is the starting point in all your analysis. So magnetostatic analysis means giving DC current into the coil and then seeing how flux distribution occurs in the machine. Always start with that. Once you know how to build and run a magnetostatic example, go into transient analysis, Maxwell transient problem example. So don't start with transient problem because that's not how you learn. Start with magnetostatic, do the first 1 or 2 examples, then go into transient problem and try to do the analysis. And just for your information, although I have shown example of only a motor, this software can also be used to model your high frequency power converters, especially your inductor, your transformer, or high frequency systems. You can carry out thermal analysis. You can also do loss analysis. So basically, you will have an advantage when it comes to research publications. So if you are doing DC-DC converter, you may not have a transformer, but you will still have an inductor. So you can do the inductive element as a part of this, carry out loss analysis and see what happens, and you can add it to your publication. That will be helpful. So it's a tool. I'm not talking about this specific vendors to simulation tool is a very useful tool, because modern day industries are going towards what is called as creating a digital twin of hardware system. So they expect engineers to be able to work with hardware, software, and a mix of both tools. And these kind of tools are going to help you in that. So with that, I will leave. So what I recommend you is to get started with the Maxwell 2D magnetostatic problem. Spend some time. That's a step-by-step guide. You may or may not be able to complete it today, but today is just a start. You don't have to worry about completing everything today. Okay. Give this a try, and if you have any questions, I'll be happy to answer. So I'll hang around at least until 5:30. Okay. Thank you. One of the analysis we are trying to do is taking these motors, we want to introduce eccentricity in these motors and see how they behave. So we are not creating the design, we are not designing the motors, right? We are using the correct design. We are just introducing a fault of our choice and we are seeing what is the impact on performance. Interestingly, we found some motors have a torque reduction due to eccentricity. So performance may not always worsen. Cogging torque worsens, but sometimes torque will improves. We have to do more research. All I'm saying is these kind of designs are also possible. So if you really look at this model, so you see here phase A is all these highlighted sections of phase A. So this is a 6-pole machine. Phase B is here, phase C is here. And the excitation, these are all current excited. Like we chose to give current excitation, but ideally voltage excitation would make more sense. Current excitation means you are circulating a fixed value of current and you are seeing its performance. How much torque can it develop? Rather than loading the motor mechanically, we are injecting current and seeing what is the torque develop, what is the regulation. Okay. So that's the idea. So and these magnets, they are magnets. So you can actually you will see the magnet type from the library. So the magnetic properties can also be edited. So if you are using a magnetic material of your choice, you can edit its characteristic. You can introduce non-linearity or you can eliminate non-linearity and you can do simplified simulation. So there are many benefits to a finite element simulation tool. What I'm saying is you now have access to as close to real world as possible with this tool. Right? You have already access to a Chevrolet Bolt motor. Now you can excite it with inverter in the software and see how it responds. You can introduce valves, you can load it with different driving cycle conditions and see what is its impact. And this is just an example. You can do like that for any different application. So that's the benefit of such tools. It will accelerate your research process. Thank you.